Okay, sigma notation is a little intimidating, but all this really means is sum. So we're talking about the sum of a series or sum of a sequence here. So to generate this is our notation, and what this means, to find the first term, we basically plug in this value. So if I wanted to find the first term of the sequence, 1 squared is 1, plus, because we're adding a sum. If I want to find the second term in the sequence, I go up by an integer. Wherever I start, I just go up by 1, so this I would plug in a 2. So 2 squared is 4. And then I plug in the next number, which would be 3. 3 squared is 9. And the last number is 4. So it went from 1 to 4. So I knew I had to plug in 4 terms. 1, 2, 3, 4. This kind of just counts from this number up to this number, and it stops. So the last term I'm going to plug in is 4. So 4 squared is 16. So I'm going to add all those numbers up. When I do that, I get 25 plus 5 is 30. So the sum of that, or the sigma notation, the sum of that sequence is 30. And I'm done. So let's try another one. So let's try this one. So this one starts counting at 3. So I'm going to plug in that first term. 2 times 3 is 6. 6 plus 1 is 7. Plus the next term I plug in, which is the next integer between 3 and 5. So 4. So 4 times 2 is 8, plus 1 is 9. Plus the last integer I'm going to plug in. There's only 3 terms in this particular sequence. 3, 4, 5. And so I stop counting at 5. 2 times 5 is 10, plus 1 is 11. And I get 27. And so that is the sum of that particular sequence. To take it a step further, I'm not sure if your book does this, but let's say we wanted to write this sequence in terms of, so let's go 3, 5, 7, 9. So if I wanted to, that's what we just did, isn't it? Very close to that. Let's do 3, 8, 13, 18. So we've got a sequence here. And let's say it stops there. There's just 4 terms. So if I wanted to go backwards and write sigma notation, I go from n equals 1. Let's always like to start at 1. That's n equals 1, n equals 2, n equals 3, n equals 4. So it goes all the way up to 4 here. And all I put here for sigma notation would be whatever the sequence is for this one. And so we know that a sub n equals a sub 1 plus n minus 1 times d. So if you want to get the sum for this sequence, you just say that's 3 plus n minus 1 times 5, because we're adding 5 each time. And so we get 5n minus 5 plus 3 is minus 2. And that's what we put here, 5n minus 2. We basically put our nth term formula inside the parentheses, the nth term formula for the sequence. And if I were to mathematically figure that out, it's the same as these numbers, 3 plus 8 plus 13 plus 18 added together. Whatever that is would be the sum of that sequence. Let's do one more. So we wanted to write something like this in sigma notation. Might be kind of hard, but how many terms are there? Well, you can see it starts counting at 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 17. So it didn't start counting at 1. So 1, 2, and 3 have been are omitted here. So there's not 17 terms in the sequence. There seems to be 3 less than that. So I think there's 14 terms. So I'd say n equals 1 to 14. That's probably the easiest way to do this. Some people start at 4 and go up to 17. But it can be a little dangerous doing that way. I think it's easier to think through this way. The formula would just be, oh, you know what? I don't think it would be easier. I think in this one, let's go from n equals 4 to n equals 17. Oh, I don't have to write the n equals on top, by the way. You just write 17. And the formula would just be, well, what am I doing in terms of n? When I plug 4 in there, I get that. So this is just square root of n. Let's double check. I always like to double check the first and last terms. If I plug in 4, what do I get? I get square root of 4, which is the first term. What happens if I plug in 17? I should get this last term. square root of 17? I do. So that is the correct sigma notation for this particular problem. And you are done.